Look at this image. If you wanted to find a picture with this specific aesthetic, a sweeping mountain vista bathed in deep orange and purple, how exactly does a machine search for that? A traditional relational database relies on rigid columns and rows. To store this picture, a human has to manually type in metadata tags like mountain, sunset, or orange. But those simple text labels fail to capture the actual context of the image. A search query for orange doesn't capture the subtle gradient of the sky, the lighting patterns hitting the peaks, or the multidimensional composition. This fundamental disconnect is known as the semantic gap. It is the distance between how computers store rigid, structured data and how human beings actually perceive complex meaning. If a computer system cannot bridge this gap, artificial intelligence cannot successfully retrieve or understand the messy, unstructured reality of human data. To bridge that gap, AI uses an embedding model. This model takes unstructured data, like our image, and transforms it into a high-dimensional array of numbers, known as a vector embedding. Each position in this array represents a specific learned feature. For example, the model might assign a score of 0.91 to indicate high elevation, and a 0.83 to represent warm colors. Now compare that to a sunset at the beach. The beach vector has a low elevation score, around 0.12, but because it shares that same vibrant sky, its warm color score sits at 0.89. When these arrays are plotted on a coordinate grid, the AI knows the images are related. The 2 points mathematically cluster together along the warm color dimension. Meaning is no longer reliant on human-assigned labels. It is now defined by measurable mathematical proximity within a high-dimensional space. Scale introduces a massive computational hurdle. Real-world vector embeddings have thousands of dimensions. When you have millions of these dense vectors in a database, comparing a search query against every single point is slow and resource-heavy. To maintain speed, databases use indexing algorithms like approximate nearest neighbor, or ANN. Instead of scanning one by one, ANN maps the vector space by dividing the entire dataset into isolated, manageable clusters. When you submit a search, the algorithm skips the exhaustive scan and snaps directly to the cluster most likely to hold the answer. It trades a microscopic fraction of accuracy for massive search speed. ANN indexing is the catalyst that turns heavy mathematical theory into the real-time retrieval engine required by modern AI. This same vector process applies to enterprise text. Corporations use embedding models to organize millions of pages of proprietary documents, from technical manuals to internal policies. This is the Retrieval-Augmented Generation, or RAG workflow. The vector database retrieves relevant text chunks, feeding them directly into the large language model. Treecapital's Anven model acts as the reasoning engine here, processing the data to trigger autonomous agents. Because the RAG architecture forces the model to reason based on your own verified documents, it keeps the output grounded in factual truth. But processing sensitive data brings up a security risk. Sending proprietary corporate documents out over the open internet to be processed by public cloud models exposes the organization to data leaks. Treecapital's solution is a sovereign architecture. Anven runs securely behind your firewall, with the entire stack living inside your private cloud. By keeping the vector database and Anven inference engine local, your data never leaves the premises, ensuring strict air-gapped autonomy. By securing the physical architecture and bridging the semantic gap, an enterprise removes its dependency on external cloud providers. You maintain total control over your proprietary data and the models that process it.